Hello, I'm your physics teacher today, and we're going to be talking about electromagnetic waves. And real quick, if you can recall, we said that there were two types of waves. We have electromagnetic and we have mechanical waves. And we talked about mechanical waves. We said that mechanical waves are made of transverse and longitudinal waves. An example of a transverse wave would be a vibrating string, like the string on a guitar, while an example of a longitudinal wave would be a sound wave. But we're not going to go into that now because that was in our previous lesson. But today we want to be talking about another type of wave known as electromagnetic waves. So what are electromagnetic waves? Well, these are waves that can travel through space. Now remember, in space, there is no medium, there is really no material. So unlike mechanical waves, electromagnetic waves do not need material in order to move. They are able to actually move through space. For example, the sunlight. We get the sunlight from the sun, and the light has to travel from the surface of the sun to the earth, and it does that through space, and it does that through a process known as propagation. Now, so what does an electromagnetic wave look like? Well, here is a 1D representation of an electromagnetic wave. It almost resembles the wave that is produced by a string. So you could say that this looks like a transverse wave. A 2D representation of an electromagnetic wave would look like this. Notice that you have the red zone and you have the blue zone, and they are at right angles to each other. So the 1D red zone would be your electric field, and then the other 1D would also be would be a magnetic field. Together they make the electromagnetic wave. In other words, the main composition of an electromagnetic wave is it's composed of an electric field and a magnetic field. So light waves is an example of a wave that has both an electric field and a magnetic field as well. Now, we have what we call an electromagnetic spectrum, and that's because we have different types of radiation in this spectrum, and they pretty much travel at almost the same speed. They exhibit the same properties most of the time. Now, to our left right here, we have what we call the long waves. At this end of the spectrum, the energy is very low, and you also notice that the wavelength is large. For example, 1,000 meters. And then going towards to your right, you come across the radio waves, which is around 10 meters and 1 meters. This is the wave or the radiation or wavelength that is used in transmitting radio signals. As you keep going further right, you come across the microwave in your kitchen, which produces the energy required to heat your food. And notice that the wavelength is small, to 1 centimeters. At this point, the energy is larger than the radiation that's to your left. As you keep moving further, you come across the thermal, infrared, and then you come across the visible light spectrum. This is the wavelength or the radiation that we're able to see with our eyes. Usually we see it as white light, but if we look at it through a prism, the white light is broken into colors. And right here at the bottom, the colors are red, orange, yellow, green, blue, indigo, and violet. And together they make what we call the visible spectrum. The wavelength for this spectrum is from 700 nanometers to 400 nanometers. So what that means is that your violet radiation has slightly more energy than your red radiation. Remember, the farther we go to the right, the higher your energy is. And then as we move further, we have the ultraviolet. And then right here we have the X-rays. Remember, the X-rays are able to penetrate the human skin through the bones. Let's go back to the previous slide. Okay, so the X-rays are able to penetrate through the bones, and that's why we use them to look inside the body. We don't want to be exposed too much because of the amount of energy, the intensity of energy that the X-ray produces is enough to cause tissue damage. And all the way to the right, at the very extreme of the spectrum, we have gamma rays, and these are very, very dangerous rays that can cause all kinds of human problems like cancer. So together they make up the electromagnetic spectrum. Okay, now remember when we talked about sound waves or mechanical waves, we introduced the speed, frequency, wavelength, and period. Well, electromagnetic waves also have the same type of variables as well. For example, we talk about the frequency of an electromagnetic wave, we talk about the speed, we talk about the period, we talk about the wavelength of an EM wave. There's one minor adjustment, unlike the sound wave, that is much smaller. The speed of the sound wave is much smaller. With the electromagnetic wave, the speed is very high. This is 3 times 10 to the power 8. So that's equivalent to 300 million meters per second, and that's really very fast. We normally say that we normally designate this speed with the letter C to represent the speed of light. So let's just quickly check for understanding here, and these are some questions you go through as you try to understand this section as we've covered it. The first question is, do EM waves require a medium to move? What do you think? How many colors are in the visible light spectrum? What are the 2 main components of an EM wave? Which of the types of radiation has the lowest energy? That is in the spectrum. When you look at the spectrum, which of the types of radiation has the lowest energy? And lastly, which of the types of radiation has the highest energy? Did you get 5 out of 5? Well done. And that brings us to the end of our show.